Hello, everybody. Welcome back to Learning as a Hobby. In this video, I'm going to be going over some of the problems from section 1.2 in John Taylor's Classical Mechanics. I posted the lecture. I posted the summary. I'm going to try to stop saying lecture notes because they're not lecture notes. I posted the summary for for section 1.1, 1.2 yesterday on the channel, so check those out if you haven't done that yet. And read the sections before you try the problems yourself. Uh, I'm going to go over a few, just like four problems from this section. There's a lot of problems in this section. There's like 23 problems, I think, but I'm going to skip most of them and like I said, just do four of them. The reason for that is most of them are vector calculus and vector geometry problems. So there's a lot of like formulas that he asks you to derive and stuff in that section. And I've either done them already, or I'm pretty sure we'll be doing the majority of them in not in Spivak, in Shiffrin at some point. So rather than repeat content, I'll hold off for doing the proving those formulas for when we get to it in Shiffrin, just because I think that's the place where that makes the most sense to have it. So I'm going to skip most of those. But having said that, there are important formulas in the exercises that you should know. So if you're not going to prove them, you should at least read through all the exercises, because there's some important information in there that's not in the actual sections 1.1 and 1.2 in the chapter. I mean, so you should. There are important formulas in there that you should know. So having said that, let me get to what the problems that I actually did. I'll bring up the whiteboard here. All right. There's two problems in section 1.2 that he tells you that you should do, and that's 1.7 and 1.15, I think. So I did those two problems, and then if you look here on my on the screen, I also did problem 116, because 1.7 says you should do that one before you do 1.7. So we'll start with that one. And then I did one more problem just for fun. So only four problems we'll do in this video. So let me start with reading 1.7, what 1.7 says, so you can get a sense of what we're trying to do. And then I'll go back up to 116. All right, so here's problem 1.7. So he asks us to prove the two definitions of scalar product r dot s as rs cosine theta, and the sum, where's my pen? And the sum ri si, I going from 1 to 3, that that's the formula for the dot product that we think of, right? R1 S1 plus R2 S2 plus R3 S3. We want to show that those are equal. All right. And again, just a note on notation in this book before we get started on this. Where's my annotation tool? Here we go. In the book, Taylor uses a different notation than at least in vector calculus that we usually use for the magnitude or the length of a vector. So for example, here for the vector r, in the book he uses boldface for it, but since I can't write boldfaced on a piece of paper or whatever, I usually use this like arrow on top to denote a vector. In the Taylor book, to denote the magnitude of that vector, he just writes the letter without, well, in the book it's just not bold-faced, but the way I'll do it is I'll just write it without the arrow. You will see me lapse into this notation just because I'm so used to it, and I probably will use it without thinking at some point. I try my best to be consistent with the notation that's used in the book, just for clarity, so things are not confusion. Sorry, things are everything is confusion, so that things are not confusing. But just be aware, in the Taylor book, these two things mean the same thing. Whereas if I mean the vector, I'll write it like that. Okay, so here. All right, so he wants us to prove that rs cosine theta is equal to r1 s1 plus r2 s2 plus r3 s3. And he says one way to do this is to choose your x-axis to be along the direction of r. So in other words, choose a convenient coordinate system. Strictly speaking, you should first make sure that the definition r dot s equals RISI, the sum of those, is independent of the choice of axes. And he says see problem 116. So that's why we're going to start with 116, because that's what 116 is about. So we'll show that the dot product is independent of choice of coordinates. So let me just scroll back up to 1.16, and then we'll go over my solution. Just move this over here so it's a little bit out of the way. Okay, so 116, there's two parts. Part A says defining the scalar product r dot s by r dot s equals, the usual formula. Show that Pythagoras' theorem implies that the magnitude of any vector is given by the square root of r dot r. So, and then there's a part B, but let me skip part B for a second, and I'll show you the proof of part A, or my proof of part A. So here, let v1, v2, v3 be a set of orthogonal vectors in R3, and let R be the vector in black. So in my picture down here, this vector is the vector R. Right, and you have the v1, actually, let me do this in a different color. You have the v1 axis over here, v2 axis over here, v3 axis over here, right? And if you look at the vector r, if you project it into the xy plane, you get that red vector, which has length r1 squared plus r2 squared, where r1 is the x coordinate, r2 is the y coordinate of that vector, right? Here, r3 is the coordinate of the z coordinate of the vector r. So in other words, r1 is the projection of r onto the x-axis, r2 is the projection of r onto the y-axis, and r3 is the projection of r onto the z-axis. Right, so the length of the red vector just by Pythagoras, because we have this right triangle here, right? The red vector is the hypotenuse, so that has length r1 squared plus r2 squared square root, and the length of that blue vector is r3. It's whatever the length of r3 is. So if we look at this right triangle here, that one there, notice that r is the hypotenuse of that triangle. So if you take the use the Pythagorean theorem to find the length of that vector, it's the square root of r1 squared plus r2 squared, because that's the length of the base, right? Plus r3 squared, which is the height. And that means that the length squared of r is equal to the sum of the sum of the squares of the coordinates, which is exactly what we thought it should be, right? So that proves that the length of the vector is not dependent on the coordinates that you use to represent it, right? So that's part A. And then in part B, they're going to ask us to prove that it's true for any dot product. So here, it is clear that the length of a vector does not depend on our choice of coordinate axes. Again, that's what we did in part A. Thus, the result of part A guarantees the scalar product r dot r equals the sum of the squares of the coordinates is the same for any choice of orthogonal axes. Use this to prove that r dot s equals, the sum formula for dot product is the same for any choice of orthogonal axes. And he gives a hint here, consider the length of r plus s. All right, so I'll show you my proof for that over here down in part B. All right, so here I'm choosing two different coordinate systems. One of them has the vector, the orthogonal vectors x hat, y hat, z hat, and here I have a different coordinate system, v1, v2, v3. So I'm writing r and s in terms of those two vectors. Sorry, those two coordinate systems. All right, so these things are equal to each other, right? Because they represent the same spatial vector. They just have different coordinates because we're using different coordinate systems. Right. So if I look at the square of the length of r plus s, just using the definition that we just proved in part A, it's the sum of the squares of the coordinates of r plus s. So in other words, you get r1 plus s1 squared plus r2 plus s2 squared plus r3 plus s3 squared. And when you simplify that, and rearrange some things, you get this, right? So, and then, do the same thing for, in terms of the other coordinate system, right? So in terms of the primed coordinates, again, the length should be equal to this, which gives you that, okay? And by part A, those two things should be equal, right? Because remember, in part A, we proved that the length of a vector is not dependent on the coordinate system that you choose, which means that, so if this is equal to this, that means that this is equal to that. And again, by part A, this is the square of the length of R. This is the square of the length of S. And so is this, and so is that. So we can actually cancel those because they're the same. And then we could divide out by 2. And that gives us that the sum of the R and S coordinates in terms of the X hat, Y hat, Z hat is equal to the primed coordinates in terms of V1, V2, V3, right? So the dot product therefore is independent of the choice of coordinate system. Right, so that's the proof for 116. Right, and now we can go on to 1.7 because that's why we're doing 116. He said prove that first. So now we want to prove that this formula, just to remind ourselves what we're doing, we want to prove that this formula is equivalent to this formula. So let me scroll down to my proof. Okay, so choose an orthogonal set of axes such that the x-axis lies along the direction of r. Again, we're allowed to choose a convenient coordinate system because all these dot products and everything are independent of the coordinate system chosen. All right, so that if the x-axis lies along the vector r, that means that r has coordinates r, comma 0, comma 0, and s has some 3 coordinates here, sx, sy, sz, whatever they are. And if we look at the quantity here, so rs cosine theta, remember theta is the angle between the two vectors, okay? We can write s as the square root of the sum of the squares of the components, right? That's what that means. And if you look over here, this part is equal to sx, in other words, the x component. And the reason we can say that is because cosine of theta is equal to sx over the length of s, or in other words, this is sx over square root sx squared plus sy squared plus sz squared. Right, and if you solve that for sx, you see that you get that thing. So you get sx squared plus sy squared plus sz squared square root times cosine theta. Right, so that this thing here is equal to the x coordinate of s. Right, and notice that r times the x coordinate of s is the same thing as r times s sub x plus 0 times s sub y plus 0 times s sub z, which is just r1 s1 plus r2 s2 plus r3 s3, and that shows that that those two formulas are equivalent. All right, and since these are independent of coordinate systems, that means it's always true, right? That's 1.7. Okay, the next one I did was not one of the recommended problems, but I figured I'd do one more just to add in, another problem into the problem set here. This is just a geometry problem, but I think it's, I don't know, it's a good one, I guess, to do. It's one of the only other ones that's not like a vector geometry or vector calculus problem in the book. So okay, so 110 says sorry, not in the book, in section 1.2, the exercises for 1.2. 110 says a particle moves in a circle centered at the origin and it has radius r with constant angular velocity omega counterclockwise. So a particle is riding along that circle that's centered at the origin, it has radius r, and it's moving counterclockwise with angular velocity omega. So omega is a constant. The circle lies in the XY plane, and the particle is on the x-axis at time t equals 0. Show that the particle's position is given by this formula here. R of t equals x hat r cosine omega t plus y hat r sine omega t, and find the particle's velocity and acceleration. What are the magnitude and direction of the acceleration, and then relate your results to well-known properties of uniform circular motion. All right, so here I'm going to start with a parametrization of the particle's motion. So that's so r of t is equal to the vector version is equal to r of t cosine omega t x hat plus r of t sine omega t x y hat. If you take the length of that vector, you get using the formula here. Where's my annotation? Okay. So using the formula that we know now for finding the length of the vector, right, that gives you r of t. And we know that because the particle is moving along a circle, its distance from the origin is always constant, right? It always has a distance of r, which is the radius of the circle. So that means that r of t has to be r, right? It has to be the constant r. And since the particle is at constant, that's what I just said. Also, d theta dt is omega, since the particle is moving at constant angular velocity. They gave that to us in the problem, which means that theta of t is a linear function of t. So it looks like omega t plus omega naught, where omega naught is the starting angle, and omega is the slope. Just anti-differentiate, and you'll see that that's what you get. Since r of 0 is 1, 0, so you want to start on the x-axis, right? Oh, and I just realized something. There's a typo here. This should be, where's my annotation? Sorry, this shouldn't be 1, 0. This should be r 0. So it's not the unit circle necessarily. It says that the circle has radius r. So we're starting at the point r comma 0, all right? Meaning we're on the x-axis. So that means that the initial angle will be 0, right? The angle of the vector r at time t equals 0 is parallel to the x-axis. Okay, so we're starting with angle 0. Whoops, let me erase that. All right, so that means that r of t is given by the formula that they wanted us to show. All right, so r cosine omega t x hat plus r sine omega t y hat. And now if we take the derivative and the second derivative, we can get the velocity and the acceleration. Maybe I should say just a word about this notation here. In physics, they usually use, let me change this to a different color so it shows up better. This dot notation is not really used in mathematics. It's mainly used in physics, and it's used to represent the time derivative. So in other words, the derivative of some quantity with respect to time. So r dot stands for the first derivative. It stands for dr, the first derivative with respect to time. So that's what r dot means in physics. And I think this notation was used by Newton, which is why they still use it in physics. So this is Newtonian notation. And the notation here with the 2 dots, that stands for the second derivative with respect to time, and so on. All right, so we get, when we take the first derivative of the formula for r of t that we just found, you get negative r omega sine omega t x hat plus r omega cosine omega t y hat. Don't forget, you have to use the chain rule for that, because those are composite functions. And then take the second derivative, you get negative r omega squared cosine omega t x hat minus r omega squared sine omega t y hat. And if you notice, you can factor out the omega squared, the negative omega squared, and that is equal to negative omega squared times the original position vector r. And what that's telling us is what we should have expected, because we know hopefully something about uniform circular motion, and what that tells us is that the acceleration points radially towards the center of the circle. Right? So when you're when satellites orbiting the Earth, for example, it stays in its orbit, provided that it's going fast enough, because it's constantly falling towards the center, right? All right, so that's problem 110. All right, this is the last problem that he asks us to do in in the chapter for section 1.2. Show that the definition of the cross product is equivalent to the elementary definition that R cross S is perpendicular to both R and S, with magnitude RS sine theta and direction given by the right-hand rule. And then he gives us a hint. It says it's a fact, though quite hard to prove, that the definition of R cross S is independent of your choice of axes. He doesn't actually ask us to prove that, thankfully. So I'll skip. We won't prove that it's true. We'll just assume that it is. Therefore, you can choose axes so that R points along the x-axis and S lies in the xy plane. All right. So here's the proof. Choose axes so that R and S, satisfy that hint, right? R and S lie in the xy plane with R along the x-axis. Then R has coordinates R 0, 0. R is positive because, lies along the positive x-axis. And S has coordinates SX, SY, comma 0. And that's because we're choosing our coordinates so that it lies in the XY plane, meaning that its Z coordinate is 0. There's no extension in the Z direction. All right, so if we look at R cross S, just using the definition for the cross product that he gave us in the book, we get this vector. And using the coordinates, let me get my pen out. Using the coordinates that we have here and plugging them into the formula, this simplifies considerably to just this vector here, R S Y Z hat. And I'm just giving that a name so it's convenient to write down, so I don't have to keep writing R S Y Z hat. I used N for this because, excuse me, because this is the normal vector. It's perpendicular to R and S, so N for normal vector. Or it's a normal vector. Okay. We haven't proved that that's property is true yet, but we will in a minute. So let's show that the right-hand rule is satisfied first. So since the sign of R S Y Z hat depends on the sign of S Y, the normal vector n, the one that I have written above, points in the direction of negative Z hat if SY is negative. That's because R is positive, right? Because of the way that we chose the coordinates. And n points in the direction of Z hat if S of y is greater than 0. Therefore, R cross S adheres to the right-hand rule convention. Okay, so that shows that property holds. Next, I show that that R and S are perpendicular, are orthogonal to R cross S, and you just plug in the coordinates into the formula for these operations, and you get 0 for both of them. And if you remember from Shiffrin, that means that they're orthogonal, right? They're perpendicular to each other. Okay, so that checks out. And then lastly, if we look at the square of the length of R cross S, by our formula for the length of a vector, it's just the sum of the squares of the components. And if you plug in the coordinates into that formula, again, it simplifies to R squared SY squared, which is equal to R squared. And then let me bring up my marker because this might be a little confusing. So this is equal to this, for a similar reason that we had in that other problem where I think it was SX was equal to like the square root of SX squared plus, yada, yada. So if you draw the triangle, you'll see that sine of theta is the angle between R and S, right? You'll see that sine of theta is SY over square root SX squared plus SY squared plus 0 squared. And if you square both sides, you'll get that this, and then multiply through by SX squared plus SY squared, you'll get that this is equal to that. Right, so it's just from the geometry. Okay, and let me just clear that. Okay, and now this thing is the length of S squared. So we get that this is equal to this. And if you take the square root of both sides, we get this equation here. So the length of r cross s is the length of r times the length of s times the absolute value of sine of theta, which is equal to sine of theta because the angle between the vectors is never more than 180 degrees. And remember, that's from trigonometry that sine is positive in quadrant 1 and quadrant 2. So in other words, from when theta goes from 0 to pi. Okay. And that's it. Those are the problems I did for section 1.2. Like I said, it's kind of short here because I skipped over most of the problems. Let me just stop my screen share for a second. Because they're mostly like vector geometry and vector deriving formulas for using vector geometry and vector derivatives and stuff like that. So he asks you to derive like formulas for like different product rules for dot product and differentiating dot product and cross products and so on. So I skipped those, but you should at least, if you haven't proven those yet yourself, you should, but you should at least look at them because those formulas are important. As I said, I have a feeling we're going to be doing those in Schifrin anyway, so I will be doing them at some point. I just don't want to be doing the same problems over and over again. So that's the end of this video. The next problem set I think is section 1.3. Let me just double check. Problems for chapter 1. So the next problem set is actually for 1.4. So in the next video, I'll go over 1.3 and 1.4, and then we'll do some of the exercises from section 1.4. Okay. I do have. I'm going to try today to get the first videos posted for my choice for a linear algebra book, and then I'm going to finish the exercises for Schifrin section 1.2, and then once all those videos are finally done, I can move back to Spivak. And then what I'll do, I guess, from here on is I'll just rotate through them chapter by chapter. So I'll do Spivak, then I'll do Schifrin, then what did I do next? Simmons, right? The differential equations. Then I'll do classical mechanics, and then I'll do linear algebra, and I'll just rotate around again. So I'll just keep going like that. So I do, one chapter in each of them every week. It sounds like a lot. Hopefully I can stick with it. But anyway, thanks for watching, guys. If you do like this, please do like and subscribe to videos, and I'll see you in the next one. All right.